All right, what about open tubes? Our last video was about closed tubes. That was actually the more complicated one. Open tubes are open. This is a really easy, good demonstration. I could just take an aluminum rod like this. This is actually open on both ends because out here is air and up here is air, and those are both have lower impedance than does the aluminum or whatever the metal is. So I can whack this on the end, and I can get this to vibrate at different standing waves for open tubes. What standing waves can I get with open tubes? Well, I can, basically they're open, so they're going to have antinodes on either end. So I could actually start here and go like to this, and I could go here and go like to this, and I could have this oscillating back and forth. If you watched the previous video, you saw the animation of that. And I'd have a node here in the middle. So I could actually hold an aluminum rod. I could hold it right here in the middle. I could whack the end of it, and it's going to vibrate. And you can hear the fundamental frequency at that particular thing. Okay, now how much of a wavelength is it from here all the way down to here? That's half of a wavelength. So if I wanted to get a full wavelength, what would I do? Well, I would take it times 2, right? I'd take 2 times the length of the tube. So for open tubes, these are open tubes. The last video was closed tubes. For open tubes, all I have to do is take twice the length of the tube to get the wavelength. Now again, do we have to deal with diameters? Yes, we do. So there's a kind of a simplified thing. You need to kind of get the effective length. And for open tubes, it's 2 times the length plus 0.8 D. Now remember, for the closed tubes, it was 4 times the length plus 0.4 D. But for an open tube, we actually have 2 openings, right? So it's going to be length plus 0.4 D for or 0.8 D for open tube. So this is the equation we're going to use here. Sometimes I might say the diameter is irrelevant, negligible. So then you just take 2 times the length of the tube to get the wavelength of the fundamental frequency. What harmonics can I get with this? Well, the fundamental is like this, right? So think of it as an X. That's the best way to do it. Think of it as an X. So I could get the second harmonic, which would be 2 X's, right? 2 X's. They're waves, but I like to think of them as X's, right? It's easier to think about. Okay, and how would I get this? By the way, how would I get this second harmonic to play on an aluminum tube? Well, I can't hold it in the middle anymore because in the middle I have an antinode. I could hold it right here, right? Or I could hold it right here. Either one. You don't have to hold it at both. But if I hold this tube right there, I would have, I'd force this to vibrate at its second harmonic. How far is that? Well, there's one, and there's the middle, and then there's another one, and then here's the end. Right? So what am I dividing the tube up into? 1, 2, 3, 4. I'm dividing it up into 4 pieces. So if I hold it down here at 1/4 of the length of the tube, I would get this to force this to vibrate at its second harmonic. Okay, what other harmonic? I could get 3. I could do 1x, 2x, 3x's. So these are waves, right? These are waves. They have to be open on the end. That's the key, right? So how could I get the third harmonic to play? Well, I could hold it here. I could actually hold it in the middle, right? I could hold it in the middle. But the thing is, if you hold it in the middle, that's the same thing as doing the fundamental. So ironically, and I could show you this on an oscilloscope, if I held an aluminum rod in the middle and I whacked it, you would get the fundamental and you would also get the third harmonic. In fact, you would also get, I'll come over here, you would also get a fifth harmonic. You get 5 X's. You get a fifth harmonic. You can get a fifth harmonic too. But these higher frequencies go away really quick. So the fifth harmonic would dissipate, and then the third harmonic would dissipate, and you'd be left with the fundamental. Okay, and you could even see that on an oscilloscope. It's really, really nice. And maybe I should actually video me doing a demonstration. I don't know if I could do that from home or not. Okay, well anyway, if you want just the third harmonic though, to maintain the third harmonic, you'd actually have to clamp it right here at this node. okay, or this one, it doesn't matter. And how far in is that? Well, this would be, you'd have this, and then you have it to there, so you'd have this, there's the end, there's a node, we have that part, we have this part, we have this part, we have the node, and we have another end. We got 1, 2, 3, 4, 5, 6. So you'd have to go in 1/6 of the way to get it to play its third harmonic. Okay? Remember, its second harmonic was 1/4 of the way in. Third harmonic is 1/6 of the way in. Want to guess what the fifth harmonic is? The fifth harmonic would be 1/10 of the way in, right? 1/10 of the way in. This number down here in the bottom is always double whatever the harmonic is, right? So what if I wanted the fourth harmonic? I could get a fourth harmonic, 1, 2, 3, 4, right? The fourth harmonic would be 1/8 of the way in. Okay, 1/8 of the way in from the edge. I could clamp it there, and I would be able to play the fourth harmonic. Okay, so these are open tubes. That means it's open on either end. And to figure out the wavelength, you'd take twice. For the fundamental, you'd take twice the length of the tube, and you can put in a diameter adjustment if you need.